Welcome back to another video. Now that we know we have a concept of the finite state machine, we will try to implement it. And like I said, indirectly, it will implement our sequential circuit. Right? Now, before we go to the actual methodology here, you know that we had that previous definition wherein a sequential circuit was viewed as, in terms of the schematic, it had a combinational part like I have here, and it had a memory in the feedback. Now we have studied memory. We know that a memory is basically a flip-flop if you have to store one bit. But in general, you have to store multiple bits. So we combine flip-flops and it becomes a register. So this thing here is what is known as the state register. Fine. I'll write it here. The state register is an, let's say, m-bit register that holds a binary number, and that binary number represents the state of the circuit. So representing the current, the present state of the circuit. Fine. And state register will always have a clock. So this is the clock. Then the output of the state register will go to the combinational logic. You will have some external inputs, previous outputs, like this, and then you have the FSM output. Fine. Now I have refined it in the sense that instead of using simple memory, now we have fine-tuned that it will be a state register, and whatever binary value it will contain will determine the current state of your circuit. These are your FSM inputs, FSM outputs. Fine. And there is a state register. Fine. And this basically is, okay, this is clock. So this is basically what we call the standard architecture of an FSM or of a sequential circuit, because every sequential circuit will have this kind of an architecture. And the only thing you need to resolve is two things basically. First, you need to know what the value of M is. I mean, how many bits you require to store in the state register. आपका state register कितने bits का है. And then second thing you need to resolve is actually आपका combinational logic क्या है, what your combinational logic is. And the entire methodology is based upon these two facts, right? So it basically is a 5-step methodology. Just remember when we did the design of combinational circuits, वहाँ पे भी we started with the general methodology first. And then we applied that methodology to design different combinational circuits. Same thing here. So the methodology that is here has a first step, and the most important step. You have to capture the finite state machine of the, I could say, capture the FSM that describes the behavior of the circuit. So the first step is capturing the FSM. So that's why we spent some videos understanding what a finite state machine is, because this is the first step of the methodology. Fine. Then second step is, once you have captured the FSM, second step is we create the standard architecture. And at this step, you should be able to tell what is the width of your state register by using a state register of appropriate width. Because from the FSM itself, you will have the knowledge, complete knowledge of how many states are there, and that itself will tell you that in the standard architecture, what is the what you call width of the state register. Fine. Then the third step is we encode the states, because for implementation we can't use the states in their original name. Like in the example that we considered, we had the names off, on one, on two, on three. I can't use these names for implementation. So every state will be given a unique code. Fine. So maybe I should write here that is encoding the states means assign a unique binary code to each state. This is the third step. Then in the fourth step, we actually, just a second. Then we take, this advantage of this coding. And the fourth step is we create what's known as a state table. Just like in combinational circuits, we have the truth table. Here it changes to state table. In fact, we had drawn state tables for flip-flops. Right? So it is just like a truth table. So it is just like a truth table. That is, we have to create a truth table that will generate the correct FSM outputs for different input combinations. Fine. And then finally, you have to implement from this table, you will come up with a Boolean equation that will implement the combinational logic of your sequential circuit. Fine. So we are basically looking for a finite state machine that captures the behavior of the circuit. Then the rest of the steps are divided in two parts. Yeah, the entire methodology is divided into two parts. First part, we need to determine the width of the state register. And the second part, we need to actually resolve this combinational logic. Right? In the next video, we'll actually try to implement the example that we considered while learning the FSM. We'll go through these 5 steps and see what its implementation looks like.